The traditional way to simulate polymers is to think about them directly in terms of real particles bouncing around. This video is meant to describe how we can derive a far more computationally efficient statistical field theory for polymers. It's meant as an overview, so if you want more information, see the papers linked in the description. The simplest polymer, that I can think of anyway, is polyethylene, a simple chain of carbon atoms shown here in red, bonded to each other forming the backbone of the polymer, and each carbon atom is bonded to 2 hydrogen atoms. For a more interesting example, this is polystyrene, where each monomer also includes a phenyl group, or benzene ring, that I've colored in yellow. There are many other examples forming all plastics, as well as biological molecules like proteins, carbohydrates, lipids, DNA, and RNA. From here, if we want to know how polymers behave, we can simply, start from here and plug in what we know about how atoms interact with each other. We know how all the atoms are bonded together. We know the bond lengths, as well as the energetic costs associated with deviating from those bond lengths. We also know the bond angles. For example, carbon atoms tend to form a tetrahedral arrangement with an angle of 109.5 degrees between bonds. These bonds can move a little, but we know the energy functionals associated with deviating from those equilibrium angles. We also know how non-bonded interactions work. That is, we know the energy is a function of the distance between atoms, and thus the forces they exert on each other. There are also dihedral angles that I've not included here, but once again, they're known. I've left off charges here, but we know how forces associated with charges work. There's some nuance to this. These energy functionals can be difficult to obtain, and precise values depend on the environments that the atoms find themselves in, and they can take a lot of work to find precisely. But for the most part, for practical purposes, these energy functions and relative interaction strengths are known, or at least well approximated. So what do we do from here? Well, if you know the energy functions and therefore the forces, it's just a matter of setting up the system and solving Newton's equations. Calculate the forces, step the precision and the velocities forward in time a little bit, and repeat over and over again. This is a simulation of a single molecule of polystyrene block polyethylene. That is, a polymer where a polystyrene molecule is bonded to a polyethylene molecule, and here it's just floating around in a vacuum. I started it with the polymer fully stretched out and just let it run. There's something kind of viscerally satisfying about watching molecular dynamics simulations, watching every single atom just move around and do its thing. It's kind of nice to see all these little atomic details, and feel like you're peering into the atomic world. You almost forget that this is just a mathematical abstraction. Molecular dynamics simulations are particularly useful in biological systems. For example, this calculation, where a ubiquitin molecule is being pulled on to see how it unravels. Seeing how proteins fold or unfold is a huge topic in biophysics. I'm interested in polymers, biological and otherwise, but molecular dynamics is a powerful technique applicable to many systems, from proteins to annealing metals. Here's an MD simulation I did of 8 molecules of Buckminster fullerene, that is 8 buckyballs just bouncing around in a box. MD is so general and so conceptually simple that your imagination is your limit. Well, kind of. There are some difficulties. For one thing, setting up these simulations, even if conceptually simple, is not that easy depending on the system you're looking at. But that's minor. If tedium stopped a scientist, we'd never get anything done. The real problem is the time and computer resources involved. One interest of mine is phase separation in polymeric systems such as block copolymers. I can easily set up a system of a melt of polystyrene block polyethylene and run a simulation close to where experiments see it forming layers. This is an example of such a run. Rather than seeing layers, however, what I get is frustration and boredom as I stare at a seemingly unchanging system. I suspect that I would eventually get layers, as that's what's seen in experiments, but I'm just not willing to wait that long. The systems that I've shown are tiny and run for very short times. Real-world problems are a bit more complicated, involving orders of magnitude larger systems and longer times. The mesoscopic polymer behavior that I'm more interested in happens on timescales to the far right of this figure, far beyond what one would use MD for. In order to go further, we have to find a faster way of conducting simulations. In the calculations so far, we've considered each atom individually. For systems with a lot of atoms, this gets computationally expensive. Rather than doing all-atom molecular dynamics simulations, we can simplify the problem by coarse-graining over sets of atoms. Rather than considering interactions between individual atoms, we can consider effective interactions between groups of atoms. In this case, I've replaced a monomer by a single bead. Rather than looking at, say, polystyrene block polyethylene as we did before, we can replace monomers by beads, and replace the interactions between monomers with ones that ideally would mimic the effective interactions between the actual monomers, and then we can run the simulation and see what happens. This simulation qualitatively reproduces the behavior seen in block copolymers, but I didn't carefully choose the interaction strength to reproduce those of polystyrene block polyethylene. In order to get the simulation to occur in a reasonable time, that is, a time that I'm actually willing to wait for, I had to fiddle with the interaction strengths, and even then it was kind of annoying to wait for it to run. But if we're going to abstract out the atomic details, creating a model that needs to be mapped onto the real thing anyway, we can do a better job. So let's try something else. I'll skip over the mathematical details in this video and give you more of a heuristic picture of the process. If you're interested in those details, there's a more mathematical version of this video as well. Imagine you have some set of particles. It could be a set of polymers or polymers in a solution or anything else really. Now pick out one of those particles. You can add up all of the interactions that it has with every other particle in the system to get the energy of that particle at that point in space. You can, in principle, move that particle around and calculate the energy that it would have at any other position in space. This creates a potential field giving the energy of the particle at any point in the system. You now have a field representing particle-particle interactions with that particle, or really that type of particle. This potential field gives you a probability distribution of where you're going to find that particle. That is, given the field, you can calculate where the particle is most likely to be. For a polymeric system, this energy is the sum of the bonded interactions, like bonding energies, bending energies, etc., and non-bonded interactions, like pairwise interactions between particles. If we can do this procedure for one type of particle, we can do it for as many types as we want. Each monomer of a given type is essentially the same, so the non-bonded interactions will be the same for each type. That is, we just need one field for each type of monomer. Similarly, each chemically identical polymer should behave statistically the same. Putting this together, we can place the polymers in the field and find their statistical behavior. The reason that we're interested in the statistical behavior of polymers and their monomers is that the probability distribution of these monomers gives us the particle density. If you have a large number of particles, then their actual distribution will be close to their probability distribution. But we said earlier that the field is obtained from particle-particle interactions. The field therefore reflects the particle distributions. And this brings us full circle. Particle-particle interactions are represented using a field. The field gives us the probability distribution of particles, the distribution gives the density, and the density gives the potential. This brings me to one extremely successful field-based approach, self-consistent field theory. Starting with a guess for the fields, you can calculate the particle probability distributions, which is then identified with the particle distributions and therefore the density, which can then be related to the field. The field is then updated iteratively until the field and the resulting distribution are consistent. That is, until we have one big self-consistent field-based picture. Self-consistent field theory has been very successful in predicting the behavior seen in experiments. The examples shown here are for block copolymers, however, this is just one of many applications for SCFT. It even predicts the topology of the phase diagram almost perfectly. You may notice that the phase diagram from theory and experiment match quite well near the top, but the bottom looks a bit different. Self-consistent field theory predicts that the disordered phase transitions to spherical phase before it goes to the other phases, whereas experiments find the boundaries between all of those observed phases and disorder. The transition between order and disorder is also pushed up as compared with theory. To see why these differences exist, we have to look back at the argument behind self-consistent field theory. We argued that once we know the probability distribution given by the fields, we know the particle distribution. But is this really true? Does the particle distribution really perfectly sample the fields? Imagine that you have some simple parabolic potential. The particle probability distribution should form a Gaussian distribution as shown here. Now let's put a whole lot of particles in the system and see what happens. I've randomly generated the positions of 10 million particles following this distribution and have plotted a histogram. This histogram, that is, the actual distribution of particles, does a good job in reflecting the probability distribution that we find from the potential. But what about if we use fewer particles? 1 million particles still does a pretty good job. At 100,000, at this resolution for the histogram, we start to notice some differences, but it's still pretty good. At 10,000, the differences become quite noticeable. If we go down to just 1,000 particles, the particle distribution is noticeably different from the probability distribution. On average, of course, the particles would reproduce the expected distribution, but imagine looking at a real physical system. The actual distribution of particles at any given time will deviate significantly from the probability distribution from that potential. The fewer particles you're averaging over, the more they will, at any given time, fluctuate away from the probability distribution that you predict from the potential. The field produced by these particles would therefore also fluctuate, which then changes the distribution of the particle sample. The overall effect is fluctuations in the density. For polymers, the longer the polymers are, the better they sample the fields and the smaller fluctuations are. Fluctuations in polymers therefore decrease as polymers get long, and self-consistent field theory becomes exact as polymers become infinitely long. Knowing the fields, and therefore the probability distribution of particles, only tells us the average particle distribution, or gives us some knowledge of the instantaneous distribution, but not enough to perfectly describe the system. Self-consistent field theory works well when polymers are long, and is rigorously accurate when polymers are infinitely long, but it still does a pretty good job when polymers are quite long, especially when the distributions are sharply peaked enough that there won't be that much deviation, like deep into the ordered phases. This is why the tops of the phase diagrams that I showed earlier look so similar between theory and experiment. What self-consistent field theory really tells you is the single most likely configuration. If we want a more accurate theory, we need to sample fluctuations around this single most likely configuration. There's a number of ways to do this, most notably simulations. We can use standard techniques like Monte Carlo or Langevin dynamics to sample the field-based model. The more mathematical details are in the mathematical version of this video, but for this video I'll spare you the details and just go to a result. This is a Langevin dynamics field-theoretic simulation comparable to the particle-based layer-forming one that I showed earlier, except that the system is clearly much larger, and I didn't have to crank up the interaction strength to get it to actually form layers in a reasonable time. I chose parameters that are close to the order-disorder transition. As before, it phase separates quite quickly into A and B domains, but they form an interpenetrating lattice, not layers. After a little while, some layers start to nucleate and they grow to engulf the system. Soon, all we have is fluctuating layers. If we use field-theoretic simulations to calculate the phase diagram, rather than self-consistent field theory, we get results that are much closer to what we see in experiments. I'll leave you with this mesmerizing simulation of a mixture of two polymers of different types. I hope you've enjoyed this exploration of polymer field theory. This way of looking at polymeric systems allows for a fast, efficient, and yet accurate way of describing and simulating polymers, and it offers insight into not only how polymers behave, but why they behave the way they do. The conversion to a field-based model is mathematically exact. The ways that it's often implemented involve some approximations, like ignoring certain atomic degrees of freedom. But for many systems, this cost is small, and it buys us the computational efficiency needed to explore large and complex systems. If you enjoyed this video, check out the other videos about my work, or better yet, read my papers. Anyway, thanks for watching and listening.